Hi there, guys. My name is Harry, also known as Zeta on TikTok. Today I'm going to be going through this step 2 complex numbers question. So let's just get right to it. Okay, so this first relation, all we have to do is multiply out the left-hand side to show that it's equal to this. So let's do just that. So we're going to have cos theta plus I sine theta multiplied by cos phi plus I sine phi. And then this is going to be cos theta cos phi minus sine theta sine phi, because you've got I times I. Yep. And then we've got plus I times sine theta cos phi, mess the phi up, plus sine phi cos theta. And this is exactly what we need, because this is, in fact, cos theta plus phi plus I sine theta plus phi. Cool. So that's the first one proved. Done. We'll say QED, just for the aura. Okay. Now, we need to prove that for every positive integer n, this equals this. This is de Moivre's theorem, so it's quite a famous theorem. So when I think I'm going to attempt induction here, so let's do it. So we prove it for the base case. So when n equals 1. So base case n equals 1. This is going to be cos theta plus I sine theta to the power of 1, which is, in fact, cos theta times 1 plus I sine theta times 1. And then we can say, so true for n equals 1. Cool. Now, assume true for n equals k. This is cos theta plus I sine theta to the k will equal cos times cos of k theta plus I sine of k theta. Cool. Now we set n equals k plus 1. Don't know why I drew a bracket there. This is cos theta plus I sine theta to the k plus 1. And then in induction proofs, you always use this n equals k part. So a way we can involve this n equals k part is we break the k and the plus 1 apart. So we'll have this to the k times cos theta plus I sine theta. And this is just cos k theta plus I sine theta multiplied by cos theta plus I sine theta. Cool. And then we know from the first part that this is cos of k plus 1 theta plus I sine of k plus 1 theta. Because here on the first part, we can just let phi equal to k theta. Cool. So k theta plus theta is k plus 1 times theta. And now, by considering this or otherwise, prove that this is true. Cool. So this is going to be to do with arguments, because we have arctan. So for example, let's say we have a complex number z. So let's say we have z, and that this is equal to a plus bi, where a and b are real numbers and I squared is equal to minus 1. Let's say a is greater than 0. This means that the argument of z is given by arctan of b over a. Okay? So this 1 over 5 is what I'm looking at here, because we've got 1 over 5 here. I mean, we've got minus 1 over 5 for the argument. So the argument of 5 minus I, is arctan of minus 1 over 5. But since arctan is an odd function, this is also minus arctan of 1 over 5. Okay? So that means that the argument of 5 minus I squared, that's minus 2. Because when we multiply them together, you double the... when you square a complex number, or when you raise it to any power n, you n times the argument. I'm not sure if that's true for non-integers. I mean non-positive integers, but yeah. So, this is good. Now, I also noticed that 1 plus I, the argument of that is pi over 4. So I think when I multiply this out, I should get this argument, correct? So, the argument of this complex number, let me just highlight it. So the argument of this complex number should be 7 over 17. So, let's see. So we have 5 minus I squared. Let's just try and multiply this out. 5 minus I squared multiplied by 1 plus I. And that will equal to 25 minus 10I. And then that's minus 1. And that is 24 minus 10I. Multiplied by 1 plus I. Multiplied by 1 plus I. And that is 24 plus 24I minus 10I plus 10. And that is 34 minus 14I. And then the argument of this complex number is arctan of minus 14 over 34. And this is minus 7 over 17. Well, this is minus 7 over 17 here. Cool. So, let me just rub that out. So that's fine. That's actually really good. So all we need to do is take arguments of both sides. So we can say that the argument of 5 minus I squared plus the argument of 1 plus I is equal to tan minus 1 of 7 over 17. This will be equal to minus tan minus 1 of 7 over 17. Cool. So this is minus 2 tan minus 1 of 1 over 5, as we stated earlier. And this is plus pi over 4. Cool. This isn't minus 14, this is plus 14. Apologies. Cool, so there's no minus here. And then this will equal tan minus 1 of 7 over 17. And then you get pi over 4 equals 2 tan minus 1 of 1 over 5 plus tan minus 1 of 7 over 17. Okay, very nice. Cool. And that's that relation proved, so that's QED. Nice. Alright, last part. We've got proof also that this is true. So, last time we had to multiply the complex numbers together. This time we're still going to do that, but I'm going to move this over to this side. Simply because I don't want to be multiplying in 1985. That sounds very long. So, what we'll be looking for is... So, I mentioned that it's B over A. So, arctan B over A. This will be our B, this will be our A for every complex number. This 3 is going to mean that this complex number is cubed. So, the equation would look something like this. It would be 4 plus I cubed multiplied by 20 plus I multiplied by, and then since I'm moving the pi over 4 to this side and I'm moving the arctan to this side, it will be multiplied by 1 minus I. Okay? So let's multiply this 4 plus I cubed out. As long as we show it's equal to 1985 minus I, we should be good. So this will be 64 plus 3 times 16, which is 48, times I. And then this is minus 4 times I squared, which is minus 4 times 3, which is minus 12, and then minus I. And then this is times 20 plus I times 1 minus I. Cool. So this is, 52 plus 47I times 20 plus I times 1 minus I. And then this is 52 plus 47I then I'm going to multiply the bracket on the right. So this is 20 minus 20I plus I plus 1. And that is 21 minus 19I. Minus 19I. Cool. And then this is 52 times 21. So 52 times 20, that would be 520 times 2, which is 1040. And then we're adding another 52, so this is 1092. 52 times minus 19i. 52 times 20 is 1040, and then we're taking away 52, so we're taking 12 from 1000, so that's minus 988i. 47 times 21, well, 47 times 20, that is 940. Plus 47 is 987. That's plus 987i. And then last part, 47 times minus 19i. So 47 times 20 is, hold on, did I do that part? No, I didn't. No, I definitely didn't. Okay, so 47 times 20 is 940. Minus 47 is going to be 800. Oh no, it's going to be 900 minus 7, which is plus, because the I times I makes a minus, minus 1, minus times minus makes a plus. This is going to be plus 893, because we're taking 7. Cool. So this is, I had to cut it because I messed up my arithmetic, but this is in fact 1985 minus I, which is exactly what we need. So taking arguments of both sides, we have that. The argument of 4 plus I cubed plus the argument of 20 plus I plus the argument of 1 minus I is going to be equal to the argument of 1985 minus I. So now all we need to do is find the argument. So the argument of this is 3 tan minus 1 of 1/4 plus tan minus 1 of 1 over 20 plus, or minus rather, minus tan minus 1 of, oh no, minus pi over 4, sorry. This is minus pi over 4. And this will equal to tan minus 1 of, this will equal to minus tan minus 1, sorry, of 1 over 1985. And then we'll rearrange this. So let me just bring this over. Just using this thing. Messed it up a bit, but it's okay. Let me just rewrite the arguments in there. Cool. Just move it to a bit more of a convenient space. Cool. So upon rearranging, we'll get that 3 tan minus 1 of 1 over 4 plus tan minus 1 of 1 over 20 plus tan minus 1 of 1 over 1985 is equal to pi over 4. Very nice. Okay. Hope you guys enjoyed. Yeah.